Welcome to Unit 7, Thermochemistry Review. Hopefully this unit should be relatively straightforward. Most of this review stuff you guys should remember from honors and Norwegians. It's information that's pretty easy, hopefully, to understand. And so we'll get started. All right, the first thing we have here is a list of some definitions you should know. The first one is thermodynamics. This is the study of energy and its interconversions, meaning changing from one thing to another. Potential energy is the energy due to position or composition. It's essentially stored energy. We usually talked about it being stored in bonds. It can also be stored in the intermolecular attractions that are holding molecules together. Kinetic energy is the energy due to the motion of the object. We're typically talking about the motion of the individual particles. And enthalpy is at constant pressure. The change in enthalpy equals the energy flow as heat. We usually talk about enthalpy in terms of the heat of the reaction. The key for this is it has to be done at constant pressure, otherwise things change. Right, the first thing we are going to talk about or review is the potential energy diagrams for reactions. So we have our two axes. The first axis is going to be labeled potential energy. This one happens to be in kilojoules. Just putting our values up there. At the bottom, we usually call that the reaction coordinate, which traces the reaction from its beginning point through its intermediate to the end. The first thing we have here is where the reactants go, or our starting materials. The reactants always have some amount of stored energy in them, so that's why they have a value in terms of potential energy, because the reactants typically have some bonds or attractions that give them some amount of stored energy. In order for our reaction to progress, the first thing we need to do is break our bonds. In order to break bonds, energy needs to go up. So we're going to have an increase in energy until we reach a max. And at that max, we refer to that as the activated complex. The activated complex is the highest energy part of the reaction. It's where everything's broken apart. Everything's very unstable because it's at this very high energy. So it's not going to last there very long. You'll see that after the activated complex, the curve starts to come back down. Well, if bonds breaking absorb energy, then this is where the new bonds must be forming. We'll then reach some endpoint of the products. Now the products are also going to have some amount of energy stored in them due to the bonds that they are creating. It should be less energetic than the activated complex, but it may be more or less energetic than the reactants depending on what type of reaction this is. Now there's two important measurements for energy that we need to also be able to calculate or look at from these diagrams. The first one is represented by this arrow. The arrow represents the amount of energy required to break all of the bonds of the reactants and get to the activated complex. The reaction can't proceed until it gets to that activated complex. So this is called the activation energy of the forward reaction. Now why the forward reaction? Because we're going from the reactants to the products. So this is how much energy it takes to get going in that direction. There's also an activation energy of the reverse reaction. This is how much energy it takes to break all the bonds of the product. So if we thought about this reaction going backwards, instead of that particular section of curve representing the bonds being formed, if I started at the products and worked backwards, I would need to break all those bonds to get to the activated complex, and then I would reform the bonds of the reactants. The most important thing here is the heat of reaction. Heat of reaction is the difference between the products and the reactants. The formula for this is typically products minus reactants, because that's our endpoint minus our initial point. In this particular reaction, my delta H is positive because my products have more energy than my reactants do. So when I subtract them, you end up with a positive number. That indicates that this is an endothermic reaction, meaning that it needs to absorb more energy than it started with. So the reaction that occurs must absorb heat from the surroundings. Energy must be added to make this reaction go. We could also have a potential energy diagram that indicated an exothermic reaction, and that is where the system releases heat to the surroundings. So here your product should end up lower than your reactants so that your delta H value would be negative. All right, using heats of formation to find the delta H of reactions. So there are such things as standard enthalpies. They're called the standard enthalpies of formation, and it's the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. For example, if I wanted to form nitrogen dioxide, I would need some nitrogen and some oxygen in their elemental form. I would add those two things together, and the amount of energy that that took would be the delta H of formation for NO2. For this particular one, it's 34 kilojoules per mole. You'll see the delta H of formation has that little degree sign, so we use those as constants for these types of calculations. We can use the delta H of formations for the reactants and products of a given reaction to find the delta H of the reaction by summing up all the products and summing up all the reactants and then finding the difference. So essentially we're doing delta H equals products minus reactants, just using this information from a given source. A couple rules here. Elements in their standard states require no delta H of formation because they don't need to be formed from anything. So they have values of 0. So for example, oxygen gas would be 0, nitrogen gas would be 0, solid lead would be 0. Anything else is usually provided to you or you've given some way to find it. So here's our practice reaction. So I have 4 moles of ammonia plus 7 moles of oxygen making 4 moles of nitrogen dioxide and 6 moles of water. So for this one, I would need to add up the products and then add up the reactants and subtract them. Since this is going to be given to you in kilojoules per mole form, you have to take into account how many moles of each thing there are. So making 1 mole of NO2 is going to take less energy than making 4 moles of NO2, so you have to take that into account. To solve for this one, I would take the amount of energy required for NO2, multiply it by 4, the amount of energy required for water, multiply it by 6, the amount of energy for ammonia multiplied by 4, and then the amount of energy for the oxygen and multiplied by 7. From my source, I have required 34 kilojoules per mole for my NO2, so that's 4 times 34, plus 6 times negative 286, and then minus 4 times negative 46, plus 7 times 0. The 0 again, because oxygen gas is its normal state, so it's going to be given a delta H of formation of 0. Do all your math and you end up with negative 1396 kilojoules, which indicates that this is an exothermic reaction. Now, in our previous unit, we talked about doing bond energy calculations to estimate delta H, and now we're doing this delta H formulation, which is slightly different. So I wanted to explain to you why the formulas for these are different. For example, in the bond energy calculations, it wasn't products minus reactants, but this one is. So why is that? So let's take a look at where delta H is on this diagram. So essentially it's the difference between the product line and your reactant line. Now in this unit, when we talk about the delta H of the products minus the delta H of reactants, that red arrow represents the delta H of the products. It's how much energy those products have at this particular reaction right here. Now the reactants are here, so that's the amount of energy that the reactants contain. If I subtract the product arrow from the reactant arrow, I should be left with that blue arrow, which indicates the delta H of reaction. We did this calculation in Regents and Honors, so this should be familiar to you. Now, the reaction we did in our previous unit with bond energy, the delta H there was equal to the bonds breaking minus the bonds forming. So let's think back. Where are our bonds breaking? Bonds are breaking here. So the green arrow represents that amount of energy. The bonds forming is represented by that arrow there. Again, if you subtract bonds breaking from bonds forming, you should still get that delta H. So we're really looking at two different areas of the curve to get the same information. Okay, so either way you do this, you should get the delta H of reaction. So depending on what information you're given, it'll tell you which one you want to use. But if you draw this diagram and figure out what's going on, you should be able to always figure out which one you're supposed to be doing and which end you're supposed to be subtracting from the other. Right, Hess's law. So in Hess's law, this is another way to figure out the delta H of the reaction. So you can use a series of simple reactions to determine the delta H of reaction for a more complicated reaction. So our example here, we have 2 moles of nitrogen gas plus 5 moles of oxygen gas yields 2 moles of dinitrogen pentoxide. To do this, you're given 3 standard reactions. We have our formation of liquid water, we have something that's making hydrogen nitrate, and we have something that's also making hydrogen nitrate. So the question now is, what do I do with all of this? So what I do with this adventure is I need to find a way to rearrange these reactions so that I end up with the reaction that I want. I want to know how much energy it takes to make dinitrogen pentoxide from nitrogen and oxygen. So I'm going to take a look at the reaction that has the dinitrogen pentoxide in it. Okay? Now, in the reaction I'm given, dinitrogen pentoxide is on the reactant side, but in my reaction that I want, the dinitrogen pentoxide is on the product side. Also, I need 2 of them in the reaction that I want, and I only have 1 in the reaction I am given. So I'm going to need to reverse and double the reaction that I'm given. Now, when you reverse and double the reaction, you also must reverse and double the delta H for that reaction, meaning I must change the sign to positive and multiply that by 2. So now I have 2 times that first reaction that I'm looking at. Now I'm going to go on to another one. So my next thing I'm going to look at was the nitrogen. Now in my reaction, I would like to have 2 moles of nitrogen. So let's look at my reaction that I'm given. I have nitrogen on the correct side. It's on the reactant side. That's where I want it. But I don't have enough of it. So what do I need to do? I need to multiply that whole thing by 4 to get 2 moles of nitrogen, which also means I need to multiply my delta H by 4. Okay, so when I do that, that's what I end up with. Now what I'm going to do is put those 2 reactions together so I can kind of see where I'm at. Okay, when I do that, I'm putting the first reaction in red and the second reaction in black so I can keep track of what's what. So let's take a look at what I still need to reduce or change. So I have my 2 moles of N2O5, I have my 2 moles of N2, and then there's some stuff I can get rid of or cancel out, but I don't quite have the correct number of oxygen gas that I need. And I also need to get rid of that hydrogen gas because I don't want that in my end reaction. So now I look at my one remaining reaction there. So in that reaction, oxygen is on the reactant side, and I want to cancel out some of the 6 moles of oxygen that I have. So I'm going to take the reaction that I have, I'm going to flip it around so that I have the oxygen and the hydrogen on the product side so I can cancel them out. And I also need to change the number of them. I need to make double what I have. This will allow me to get rid of the water and the hydrogen and reduce the oxygen. Okay, so when I do that, I'm also going to need to do that to my delta H. So now I'm going to put everything into one big reaction. Okay, so I've multiplied everything through, everything is all set. My last reaction is now in green. So now I'm going to go through and make sure that I can cancel out everything that I don't want. So I'm going to have 2 H2O liquid there. I can cancel it out on the other side. I'm going to cancel out my 4 moles of HNO3, 4 moles of HNO3, get rid of my 2 moles of hydrogen, 2 moles of hydrogen. Now the next things I can't cancel, I'm just going to reduce. So I get rid of the O2 there, and that changes from a 6 to a 5. Okay, now everything that's left is everything that I want in my final reaction. I also need to then add up all of my delta H's that I have together. So I'm going to have 2 times 76.6 plus 4 times negative 174.1 plus 2 times 285.8, which gives me 28.4 is my final answer. So that's how you do Hess's law. It's kind of like a puzzle. You got to figure out what goes where, how many of each thing I need, and make sure that everything cancels out at the end to give you your final desired reaction. The next major topic is entropy, delta S. So entropy, again, is the measure of a molecular randomness or disorder. In order to predict entropy change, we look at 2 things. We look at the phase change that might be going on, and we look at the number of particles that are on our reactant side and our product side. Gases have the most entropy, and solids have the least in terms of phase. Liquid and aqueous are pretty much the same. I would say aqueous probably a little bit more because there's more particles dissolved. An increase in the number of particles also increases entropy, or is called a positive delta S, because the more particles you have, the more likely they are to be random. So let's look at a couple examples. First one here, we have 2 moles of hydrogen plus 1 mole of oxygen makes 2 moles of liquid water. So there's 2 things we can look at here. First phase. We're going from gas to a liquid, so that should be a decrease in entropy because liquids have less randomness than gases do. We're also going from 3 total moles to 2 total moles, so that's a decrease in entropy, or negative delta S. Second example, we have 2 moles of ammonia goes to 1 mole of nitrogen plus 3 moles of hydrogen. Now you'll see in this one that the phase doesn't change, it's always a gas. But if you look at the number of particles, I have 2 particles of ammonia on the reactant side and a total of 4 on the product side because I have 1 nitrogen and 3 hydrogens. So that shows an increase in entropy or positive delta S. So those are the 2 things you look at, phase and number of particles. All right, spontaneous reactions. So spontaneity is determined by 2 factors, the enthalpy of the reaction and the entropy of the reaction, meaning if it's endothermic or exothermic, and if it shows an increase or decrease in randomness or disorder. Generally, reactions that are exothermic are spontaneous, and reactions that are increasing in entropy are spontaneous. So if you're exothermic and your delta S is going up, you're definitely going to be spontaneous. The trouble lies with reactions that are exothermic but have a decrease in entropy, or those that are endothermic and have an increase in entropy, because you don't know which one's going to win. For example, when you do a phase change of water, if you're trying to change ice to liquid water, that's an increase in entropy, because you're going from an ice, which is an organized structure, to something that flows, so that shows an increase in the randomness of the particles. But to change ice to liquid water, you need to add energy. It's an endothermic process. So is this going to be spontaneous? Well, does ice change to liquid water on its own? The answer is sometimes. Sometimes it does, but it depends on something. It depends on the temperature. Above 0 degrees Celsius, this process becomes spontaneous, but below 0, it's not, which leads us to free energy, or Gibbs free energy. The formula for Gibbs free energy is delta G equals delta H minus T delta S. Here, T is the temperature in Kelvin, because it can't be negative for this formula. The H is the enthalpy of the reaction, and the delta S is the entropy of the reaction. Delta G stands for Gibbs free energy. When delta G is negative, the reaction is spontaneous because there is free energy left over to do work. So we need to be able to predict the sign of delta G given the delta H and the delta S signs. This means we should be able to predict whether a reaction will be spontaneous or not based on what we're given about our delta H and delta S. In your textbook, they'll give you ways to calculate delta S by giving you delta S standard of formation, kind of like the delta H calculations we've already done. So just as a reminder, here's the formula we're working with. Okay, and delta H and delta S can either be positive or negative, so we have 4 different possibilities here. Let's go through the first 2. So if your enthalpy is negative, that means it's exothermic. That's favoring spontaneity. If your delta S is positive, that means it's more random, which is also favoring spontaneity. Now take a look at your formula. If your delta H is negative, okay, and your delta S is positive, you have a negative minus a positive. There's no way for you to get anything other than a negative delta G, which means that this reaction will always be spontaneous. There are no exceptions to this. Now let's go through the other situation. If your enthalpy is positive, that means it's endothermic. That does not favor it being spontaneous. If your entropy is also negative, that does not favor it being spontaneous because it makes it less random. Here, let's go back through our math. If your delta H is positive and you're doing minus a negative, that means you're going to be essentially adding it. So the only numbers you can get here are going to be positive, which means that this will never be spontaneous because your delta G value will always be positive. Now the last 2 options are the tricky ones. So let's say that your delta H is negative. That means it's exothermic, favoring it being spontaneous. But your delta S is also negative. That means it's favoring it being not spontaneous. Here, you don't know. There's no way to predict unless you know the actual values. So this is spontaneous sometimes, and it depends on the temperature. So let's think about what that means. Okay, to be spontaneous, we want the enthalpy factor to win. We want the delta H value to be more important than the delta S value because it's the one that favors spontaneity. So we want to make that delta S value as minimal as possible. To do that, we want to keep our temperature value pretty small. So when you multiply it by the delta S, it just reduces that number down. So we want to keep it at low temperatures because that reduces the importance of the entropy factor. So this Gibbs free energy will be negative with low temperatures and positive with high temperatures. So these are reactions that are spontaneous at low temps, but not spontaneous at high temperatures. All right, one last case. Here we have a positive delta H, which means it's endothermic, not favoring it being spontaneous. It's got a positive entropy, meaning it is favoring it being spontaneous. So again, we don't know. Still depends on temperature. But this time, which factor do we want to win? Do we want the delta H to win, or do we want the delta S to win? For this one, we want the delta S to win. So to be spontaneous this time, we want the entropy factor to win. So here, we want to keep the temperature as high as possible because that enhances the entropy factor. So this delta G will be negative with high temperature because that's when the delta S will win, and it will be positive with a low temperature because then the enthalpy factor becomes more important. All right, that is the end of the review section. So thermochemistry is covered in those chapters in your book. You should do the outlines for those chapters for your own purposes, and there's a good deal of new information in these chapters that you're going to want to see before I talk about them in class. You should also start the bookwork when you finish your outlines. Some of the bookwork should be good review following this video, but some of it should be new for you. Hopefully the outlines will help you. All right, good luck.